today is all about chapter 6, working on those practice problems. I did move the homework quiz to Sunday. It was originally due yesterday on the syllabus, and I sent out an announcement for that at the beginning of the week. So it's due Sunday now instead, and that's what we're going to learn about today. So use the PowerPoints. I have another video working problems, and then this video as well. So there's 3 different things to help you get through this homework assignment. Discussion board's due Sunday, and there's an extra assignment that's normally not due, and that's going to be the physics assessment. This is extra credit, but you only get extra credit for the ones you get correct, not just for doing it. We're trying to assess or see how well you've absorbed the material we've taught you so far. So it's on all of this stuff we've taught you so far, starting from chapter 1, all the physics stuff. So we're doing it now because after this chapter, after this exam, we're switching to chemistry. So the last of the physics stuff. So let's start. We are going to be doing number 5 on the chapter 5 and 6 practice problems. And it's asking about the strength of an electromagnet is dependent upon what 2 things. So I talked about an electromagnet in the PowerPoints, went into a little more detail, but I want to show you one and how it works. So an electromagnet is when you have a current running through a metal core. And by having this current running through it, you're actually magnetizing that metal core. And the simplest form of an electromagnet would be a battery and an iron nail. So how it works is you have the battery, which is the voltage source, causing a current. And then you have an iron nail, which is the metal core. Now, if you take a copper wire and you wrap it around that iron nail, it's going to allow for the current to run through the copper, thus going through the iron nail, making the nail magnetized. So it can now pick up magnetic, or it can pick up other metals. And the strength of this electromagnet depends upon 2 things. It's going to be the number of coils, so the number of times I wrap that copper wire around the nail, and then also my voltage source, because that's going to affect my current. So bigger battery, essentially, stronger magnet. So I have that here, and it's a little rusted, but I did try it earlier and it works. Not as good as if I had a chance to use some sandpaper on it, but I have an iron nail with copper wire around it. This is just electrical tape to hold it kind of together. The reason I have a glove is because the ends just get a little hot. So what I'm going to do is I'm going to connect this copper wire to both ends of the battery. You'll notice right now, the iron nail won't pick up any paper clips. It's not magnetic. But when I connect it to the battery, it'll become magnetized to that current, and it'll be able to pick up those paper clips. This usually takes a minute because you have to get the ends exactly in the right spot to cause the electric current to flow. Because you need a full circuit. That's part of what we were learning in the PowerPoints as well, is you need to complete the circuit, otherwise no current will flow. So now I've connected it. Maybe. Oh, come on. I think I've connected it. Oh, let me try the little battery. I might have used all that guy. Hey, just in time to see a magnet, hopefully. I did this earlier and it worked, so it better work again. Anticipation's king. Right. I just had a bad battery. So that battery must be dead. So now it's magnetized because of the current going through it, and it'll pick up paper clips. And the stronger the magnet, the more paper clips it would pick up. So if this battery was fully charged, since it's a larger battery, more voltage source, it would pick up, be a stronger magnet essentially. And you'll see once I disconnect, the paper clips start to fall. It takes a minute because the current's running out and it's slowly being demagnetized. But it will go back to being a normal iron nail. It is now. So that's an electromagnet. If I had more coils or stronger voltage source, it would have been a bigger magnet. So moving on to the next one, explaining how a compass works. We're using magnets again to explain it. So with magnets, they always have a north and a south pole to them. How a magnet works is because of the fact that opposites attract. So what that means is whether you have a positive and negative charge or a north and a south pole, as long as they're opposites, they're going to attract. If they're alike, they're going to repel. So how a magnet works is, or how a compass works is there's a magnet inside the compass. And the needle of the compass points north because of that north end of the magnet, pointing it north. So when it's pointing north, it's pointing to the north pole of the Earth. Now, the Earth itself has this iron ore core in the center. So it's actually magnetized. The center core of Earth is magnetized. And the reason that the north end of a magnet in a compass points to the north pole is because it's actually the magnetic south pole, because opposites attract. So it has to be the magnetic south pole, otherwise the north end wouldn't be attracted to it, and the needle wouldn't be pointing towards the north pole. So the trick with this is that the magnetic south is the geographical north, and vice versa. That's kind of a simplified way of explaining how a compass works, but it's basically just magnets. The magnet in the compass, and then the magnetic core of Earth being attracted to each other. All right, now number 7 is another concept question, and we'll do some calculation questions as well, but I did want to show some of these concepts. Help them stick in your head a little bit better than just talking about them. So this next one is, if two opposite charged particles are close together, what can we say about the force between them? So I want to explain this, positive and negative charges, by using an induction example. So when we talk about induction, induction is when you induce a charge on a neutral object. So one of the examples that I used in the PowerPoint is if you have a sphere and it's neutral. Neutral, and when I'm talking about neutral, I'm talking charges. So if it has the same number of positive and negative charges, all neutral. I got positives, I got negatives everywhere. Then, if you take a charged object now, so this object here has all negative charges, and you bring it close but not touching to the neutral object, you're going to induce the opposite charge because opposites attract. So if this negatively charged object comes close to the neutral object, all the positive charges are going to come to the surface, pushing the negative charges towards the back, out of the way. Because those positive charges want to be close to that negative charge. So they're attracted. Okay? Now, the closer you bring this object, the more force is going to be felt. So the question to answer this, and you'll see in a minute as well, what can we say about the force? The shorter the distance, the more force. Okay, and we'll see that here in a second. So what I'm going to do, this is my neutral object. It's a can. It's got the same amount of negative and positive charges. If I can get it to stay still. Now this is a balloon. It's also neutral at the moment. But if I use what I know about static electricity, I can induce a charge on this balloon through conduction, direct contact, by rubbing them together, creating some friction, some static electricity. I'm rubbing electrons from one object to the other. So now, when I bring this charged object close to the neutral object, I'm going to induce the opposite charge, and opposites attract. Notice when I have them far apart, nothing's happening. But the closer I bring it, now they're starting to feel a charge, and it's going to follow the balloon because opposites attract. One is positively charged, one is negatively charged. So the distance, the closer I got, the more it felt and actually started following. Any questions so far? Okay, so that kind of sums up most of the concept questions in this packet. So that was number 7. So now what we're going to be looking at is using the equation sheet that I passed out, the chapter 6 equations and conversions we're going to use to solve most of the rest of the problems. There are, I think there's another concept one's stuck in there somewhere. But the next few are calculations. So for number 8, we have a police scanner. And this chapter is all about voltage, current, resistance, electricity, magnets, all of that stuff. So we can still approach these though the same way that we have done before by writing our list. And the variables that we have in this chapter, I'm just going to write all our variables down so it can kind of help us figure out what goes where. So we have V for voltage, and that's measured in volts. And you can see I kind of have like a cheat sheet on the equation sheet to tell you what each letter stands for. I is current, and it's measured in amps, capital A. We have R for resistance, or resistors, and that's measured with that funky symbol, the ohm symbol, O-H-M. We also talk about power in this chapter. And just like in previous chapters when we talked about power, it's still in watts. What else? Time and energy are the other two, right? Okay. Bring these out of the way. So we have time and energy. Time is still measured in seconds, just like previous chapters. And energy measured in joules. And when I talk about energy, for this chapter it's electrical energy. Previous chapters have been kinetic energy, potential energy, work energy, but it's still all joules. Okay, so we're not changing the units, we're bringing in more equations to calculate different types of energy. So given all of these, this is all the variables in this chapter, when we approach a problem, we can list them with the appropriate variable, using their units if necessary. So a police scanner uses 10 volts. So 10 volts is a voltage, so that's going to be my V. With a current, so it tells you it's a current, so that's going to be your I value. If you didn't know, it says it's amps, so you could have looked at the units to figure out that it was a current. And then we're going to calculate the resistance, so that's the R value, and it's going to be measured in ohms. So when you look at your equations, you want to pick one that works. And we only have one equation that has all three of those variables. And that is V is equal to IR. So we need to rearrange that equation to solve for R. So if I want R by itself, I'm going to divide both sides of the equation by I, because I want to get rid of it on this side. By dividing by I over I equals 1, they cancel. This makes my equation to solve for resistance, V divided by I. Now I can plug in. I have my 10 on top and my 1.5 on the bottom. I don't have my calculator. It's only one sig fig, which is going to be weird, but what do you get?
7.
7. And then for resistance, for units, it's ohms. You can write OHM, or you can make that funky symbol. Your choice. Usually I spell it out, OHM, on exams and quizzes, just because trying to find that symbol is kind of difficult. Okay. So let's look at number 9. So number 9, we have a human going into cardiac arrest, and a defibrillator, can't talk, is used to sending 700 volts into the person's body with a resistance of 75 ohms. Calculate the current. Okay, so making our list, we have 700 volts is the first number I see, and that's a voltage. That one's easy to remember because the units are volts and it's a voltage. Resistance of 75 ohms, so they tell us that that 75 is a resistance. And then they want us to calculate the current, and the current's the one that's kind of hard to remember because it's the letter I. But it is what it is. So when we solve for this, the units for current are going to be in amps. We're using the same equation. Notice we have the same variables as the previous. So we're still using that V is equal to IR. We have to rearrange it again, but this time we want the I by itself. So to do that, we're dividing again, but this time by R. This is going to get rid of the R on one side of the equation, and it will transform it so that to solve for current, we take the voltage divided by the resistance. So, plugging in our values. Looks like 1 sig fig again, kind of getting weird. You can tell I'm slacking on sig figs when I'm not paying attention to them when I'm writing the problems. Okay, so 700 on top, and we're dividing that by the resistance of 75. You can give me more than 1 sig fig. What did it say?
9.3 repeating.
9.3 repeating? Okay, we'll leave it at 9 then, since that's a nice one. I do pay attention to sig figs when I make the exams. It's just these ones I don't usually solve them before I show them to you in class. So I don't see the sig figs until I'm doing it on the board. So 9 amps of current went through that person's body. Hopefully revived them, I guess. All right. So now we're moving on to a different equation. And I know that when I look at number, oh, sorry, I need to do number 10 before I move on to 11, don't I? In which circuit would you expect a reduction in available voltage as more and more resistances are added? Okay, so let's look at the circuits. Try to explain this. So we have 2 different circuits that we talk about in this course. We have a series circuit, and we have parallel. In parallel, and I'm going to explain this using a light bulb theory because it's a little bit easier to see. So where we get this equation, this V is equal to IR, let me rewrite it, is because of circuits. Okay, we have a voltage source, which is represented by this thing here. So this could be an outlet where you get voltage from, current from. This could be a battery, like I just showed you with the electromagnet. It's just some sort of voltage source. Then you have the resistors. So that's what these little squiggly lines represent. In this series circuit, I have 3. And the thing about a series circuit is that from the voltage source comes the current. Okay, so this is my I, this is my current. With series circuit, the same current is going through all 3 resistors. So what that means is this voltage is additive. So if I keep adding more resistors to a series circuit, if these were light bulbs, you would see the light bulbs dim. Because since the voltage is additive, they're getting less voltage as I'm adding more resistors. Okay? For a parallel circuit, my green, so this would be the same. We have 3 resistors, but the difference is when the current comes through, it splits at each injunction. So what that means is it's not the same current going through all 3 resistors like it is over here, because it's splitting. So if I add more resistors, it doesn't matter because it's a different current going through each one. The light bulbs are going to stay the same brightness. It's not going to affect it at all. Also, if I took out one of these light bulbs, the rest of the light bulbs in a parallel would remain lit because I'm not breaking the current at all, because it's a different current going through each one. For series, if I took one light bulb out, I just broke the circuit, broke the current, can't flow anymore, all the light bulbs in the entire series go out. So for this question, it's asking about the voltage. Which circuit would you expect a reduction in voltage as more were added? It would be series because, as we said, if I'm adding more light bulbs, they're going to get dimmer because voltage is additive. So I'm making the voltage smaller and smaller and smaller for each resistor as I'm adding more resistors. So this would be the answer for number 10, series. Questions about the 2? And we're going to be calculating, I might leave those pictures up because in a minute, after number 11, I think we actually calculate the resistance of a series circuit versus the resistance of a parallel circuit, so we can see how those relate as well. that's not until number 12. So let's do number 11 over here. I'm going to jump to power for a minute. So number 11 is interior light of a car uses 8 watts. Now I know I erased all those variables, but hopefully you wrote them down. And watts is going to be the letter P for power, because that's what we measured watts in. We even did that, I don't know if it was last chapter or the chapter before, but we've done power before, and we've always measured it in watts. We've sometimes converted it to horsepower after, but it's initially measured in watts. So we have a power of 8, and then we have a current, so that's I, of 0.67 amps. Calculate the voltage needed to power the lights. So this isn't going to be my V equals IR equation, because I need an equation with power in it. And the power equation that I have, if you look down under the electrical energy and power calculations, I have P is equal to V times I, right? Voltage times current. So yes, I'm going to have to rearrange it to solve for V. So if I want V by itself, I have to get rid of I. Since I'm multiplying to get rid of I, I'm going to divide. Whatever I do to one side, I have to do to the other. So current cancels out on that side of the equation, leaving me to solve for voltage by taking the power divided by the current. 8 divided by 0.67. So what is the voltage needed to power the lights? Let me count this one.
11.9.
I know it's the correct significant figures, but I'm going to round it to 12. All right, so that was kind of a side problem with power. Number 12, we're coming back to these series versus parallel circuits using resistance. 12 and 13, actually. So I'm going to erase this to do the problem over here so that you can get a visual of what exactly we're solving for. So number 12 is saying we have 3 device chargers, a phone, an iPad, and a laptop. And then they give us the resistances of each. So they're plugged in to an outlet that's placed in a series, providing 5 volts. Okay, so we're going to calculate the combined resistance and the current. All right, so they said series. So what that means is there's 3 of them. They have 2 ohms, 5 ohms, and 8 ohms. So that means one is 2 ohms, one is 5 ohms, and one is 8 ohms. And the nice thing about a series circuit is, yes, voltage is additive, but the resistance is additive as well. And you can see that, additive, spelled that wrong, but you can see that when you look at the equations. So if you look under the circuit calculation equations, there's 2 different equations to solve for resistance when you have more than one resistor. There's for series circuit one and a for parallel. So we're looking under the for series circuits, and you'll notice to calculate your R total for series, you simply add the resistors together. And that's it. And you'll also notice there are dots when you see that equation. The reason for the dots is because you're going to put however many R values that there are in the series. So if you had 10 resistors, you would have R1, R2, R3, all the way to R10. You would be adding. In this case, there's just 3 of them. So to calculate my total resistance, I'm going to take the 2 plus the 5 plus the 8. Make it 15 ohms. So that is for my series. So I've calculated the combined resistance, but number 12 also asks for the current. Because remember with series, it's the same current going through each of the resistors. So we can calculate that using our V equals IR if we know enough information. The key here though is before when we used this problem, we had just one resistor. So now, since we have more than one, we need to use our R total, where R is, what we just calculated up here. So we have R total, we just calculated that. Did they give us anything else? The voltage? And they want us to solve for current. So we're rearranging the equation to solve for I. So I by itself, that means we're dividing by R total. So we'll get V over R total. I feel like I rearranged that equation 5 times today, is why I didn't show the steps. But if you're curious, I know it takes a while to remember these steps. That's how we get upon it. So now we can plug in 5 on top, 15 on bottom to get, what is that, 33333? 0.3 units amps. So total resistance, 15 ohms. The current going through it, 3.3 amps. So the reason I'm leaving that up is because the next one, number 13, we're going to be doing R total again, but instead of for the series circuit, we're going to do it for parallel. But we're using the same resistors so that we can compare them directly. So my R1 is 2 ohms, my R2 is 5 ohms, and my R3 is 8 ohms. But this time, notice we're not calculating current for this one because it's a different current through each of the resistors. So we would have to calculate current 3 times individually for each resistor. So I'm not having you do that, but I do want you to be able to calculate the total resistance of them. And the resistance for parallel, it's not directly additive, because if you look at the equation, we have 1 over R total for parallel. And that's equal to 1 over R1. And since we have 3 of them, I'm going to do 3. 1 over R2, 1 over R3. So let's see what the total resistance is for this one. Now when you solve for this, once you add these 3 fractions together, that's not your final answer. You have one more step after that, and that's to take the inverse. So I'm going to have 1/2 plus 1/5 plus 1/8. And there's no way I can do that one in my head. Can someone just add those fractions and tell me what they get? Good find it, Tom.
Oh,
Go ahead.
0.825.
So this is not your R total, this is your 1 over R total. Okay, so you can look at 0.825 over 1 is what 1 over R total equals. So to figure out R total, we need to flip this. So R total is going to equal 1 divided by 0.825. We're basically flipping that fraction. There's actually a button on your calculator that does that for you. So if you don't want to flip this and then divide 1 divided by 0.825, once you get this answer, if you press your X minus 1 button on your calculator, that's going to flip the fraction for you.
So should it be 1.2?
Yes.
Yeah, okay.
Yes. So it should be 1.2 amps. Or not amps, ohms. So notice the resistance is less for a parallel circuit with the same resistors than it is for a series circuit. Because in a series circuit, the resistance is additive. And that's part of the reason that the light bulbs are going to get dimmer. They're blocking the voltage more than here where it's splitting. Questions on this at all? This is usually the one people get wrong the most. It's a parallel circuit. Because I will put 0.825 as one of the answers, and you see that and you're like, oh, I'm done. It's on there. No, you still have to do one more step to get the final. Okay, so be careful on those ones. All right. What do we got next? pros and cons. So good thing this picture's still up. Pros and cons of series versus parallel. Well, we talked about it a little bit already. We haven't really talked about any pros with series though. So a pro with a series circuit is it's cheaper. It takes less power, less voltage. It's not going to cost as much. Tons of cons. I mean, if one of the light bulbs go out, the whole string goes out. They don't do this anymore, but Christmas lights used to be on a series circuit. And if one of those lights went out, one of the bulbs burnt out, the whole string died. Okay. Now you can see even with the Christmas lights, they have like 3 different wires combined because they're trying to make it more of a parallel circuit so that doesn't happen. But not a lot of series circuits anymore. For parallel, well, the con would be that it's more expensive. Pro is all of them won't go out if just one goes out because you have that different current going through each of the resistors. All right. So 2 problems left. Number 15, which requires more energy? So we're looking at energy now. We haven't used the energy equation. I think we have 2 equations left we haven't used, and energy is one of them. So which one has more energy? Actually, I'm looking right. So we're going to be using it twice because they're asking about a vacuum cleaner. I spelled vacuum cleaner wrong on there. I apologize. Vacuum or computer. I'll write those 2 separately because we're going to do 2 different calculations and compare. So for a vacuum, they're asking us, the vacuum has 1,400 watts. That's how much power it uses. How do I know that's power? Because of the units. Okay, watts tells me it's power. It's on for 7 minutes. 7 minutes being a time. And then it's the energy that we're looking for. That's what the very first sentence said. What requires more energy? So that's why energy is the question mark. When I solve for it, it's going to be in joules, just like when we did kinetic energy, potential energy, and work energy. For the computer, so they're going to give us the same information, power, time, and we're looking for energy. The power is 125 watts. The time that it was on is 75 minutes. And then the energy is what we're looking for. So, notice in parentheses it says, don't forget to convert time to seconds. Because time needs to be in seconds whenever we use it in physics. So, we're going to take that 7 minutes and convert it to seconds. How do we do that? We're going to times it by 60. And what you're actually doing is dimensional analysis without realizing it. Because by timesing it by 60, you're using a conversion factor that says 1 minute is equal to 60 seconds. So if I have 7 minutes, put the 1 minute on the bottom and the 60 seconds on the top. And most people just know, oh, I just times it by 60. But why? This is why. Because of dimensional analysis, because you're canceling out the minutes. So what do we get for the seconds?
420.
420. You? Down here, we're going to do the same thing. Timesing it by 60. It's a big number. No, you're fine. I appreciate you doing that.
It's 4,500.
4,500. So convert first, then look at an equation. In the energy equation we have, or electrical energy, because that's what this is, we're plugging in a vacuum, we're plugging in a computer, it's all electrical energy. We're taking power times time. Don't even have to rearrange it, just need to plug it in. So, vacuum cleaner. 1,400 times 420.
Is 588,000.
The units, once again, are joules, because it's an energy. For the computer, we have 125, so it takes less power, but notice they have it on much, much longer. 4,500 seconds.
You get 562, 500.
And I forgot if it's asking can have more or less, which requires more energy. So we're comparing the two. Is it the vacuum or the computer?
The back.
Vacuum. Not a ton more. No, so I thought 26,000 joules, but it is more. This leaves one last equation that we haven't used and one last problem. So, for number 16, we're taking this energy power to the next level, and we're going to calculate how much it costs, money-wise, to use a washing machine for a 60-minute cycle. So let's write down the information they give us and then kind of go from there. So we have the washer, well, let's start with the time. They gave us 60 minutes. And then we have the washer is connected to a 220 volt outlet with 20 amps. So what is 20 amps? What variable?
Current.
Current, which is an I. You know that because of the units, amps. The cost of electricity, and this is something we don't have a variable for, is 18 cents per, so that's what that line means, per kilowatt hour. All right, so whenever you have a cost calculation, when it says money, how much money does it cost? You'll notice at the very bottom of your equation sheet, you have a way to solve for it. And that is the electrical cost calculations. So the first step for an electrical cost calculation says, convert to kilowatts. Do I have watts anywhere?
No.
No. So first thing I'm going to do is solve for watts. Okay, and watts is power. So I have power is what I'm trying to solve for, so I need to find my equation. The only one I have in this chapter is the power is equal to voltage times current, and that's what I need with the voltage and the current. So I don't have to rearrange this equation, I just need to plug in my voltage value and my current value. So my power is going to be 220 times 20.
4,400. Oh,
I didn't know how I was trying to figure it out. I appreciate the backup though. So 4,400 watts. Okay, so this is how I'm starting my electrical cost calculation. So my very first step says convert watts to kilowatts. And it even gives us a conversion factor to do that. We have 1 kilowatt is equal to 1,000 watts. You'll notice it's also metric to metric, so if you prefer, you can just move the decimal point as well using that King Henry Dye drinking chocolate milk system that we learned about. And whatever goes in this empty space is what letter is in common between the two, so that would be W, watts, watts. So either way, this way you would move the decimal point 3 times, or you could do dimensional analysis way. So we're starting with 4,400 watts. We need to get it into kilowatts. If I use the conversion factor, this guy here, I'm going to put the 1,000 on the bottom and the 1 kilowatt on top, so that the watts cancel because of this line being a division line. Dividing that, 4.4?
Yes.
Okay. So this is now in kilowatts. So step 1, done. Now I move on to step 2. And step 2 tells me calculate the kilowatt hours. So it says take the kilowatts and multiply it by however many hours that light or machine or whatever was on. Okay, so the kilowatts we have from the previous step. That's the whole reason we needed to convert it to kilowatts. But where's our hours? So looking back, that would be a time. And it was on for 60 minutes. So how many hours was it on?
1 hour.
1 hour. You don't have to do the conversion factor to figure that out. Because that would just be 1 hour is equal to 60 minutes. That's essentially what you just did though in your head. So we multiply it by 1. That's how many hours it was on. So you would have to convert, if the time wasn't in hours, 2 hours to do this part. So 4.4 times 1, that one I know I can do. I'll go to a calculator. And notice I'm changing the units because I took the kilowatt units and I multiplied them by hours. So this is my kilowatt hour. That's what that dot means, it's multiplying the units. Now the last step, is what I need this little factor for. It's saying 18 cents per kilowatt hour. So the last step tells you to take your kilowatt hours that you solved for in step 2. Notice there's a trickle effect here. Step 1, you get an answer that you need to use to calculate in step 2. Step 2, you get an answer that you start your calculation with in step 3. So the third step, we're starting with what we ended with in step 2, our kilowatt hours. And then we're going to take this to figure out how much it costs. And to do that, we're going to multiply by it. Because what we're multiplying by is that 18 cents, that 0.18, if I'm writing it in the dollar sign way. 18 cents, and the per kilowatt hour, that means divided by kilowatt hours. So the reason we're multiplying by that factor is actually so that the kilowatt hours cancel. Because that way, once we multiply these two, we know money, cents, how many dollars it costs. So 4.4 times 0.18. It's going to cost less than $1, I hope.
Yes, 792.
So we'll round to 79. So it costs 79 cents or 0.79, a little less than $1. So that's how you solve one of those. There is one of those on the homework for sure. I can't remember if there's one on the exam or not. But the exam is coming up. Next week is the review. So this is the end of the new material. And next week I'll just be reviewing both chapters 5 and 6 for you to take your exam, which will be due next Sunday. So this Sunday, physics assessment. Chapter 6, homework quiz and discussion. You have 3 things this week. Physics assessment, by the way, since it's extra credit, I recommend you do it because that will probably be your only extra credit opportunity other than an extra question on an exam.